Okay, so we are starting now, picking up. This is part B or part 2. So let's go ahead and switch over to Scholar. Right, so we are in Scholar. So what I want to do now, remember, is we have the data, right? So we ran the script here, create vector space model. We went from 7 by 13 to 7 by 2. The advantage of 7 by 2 is that we can now visualize this data. As I said, visualization doesn't always give you so much in big problems, but it's yet another tool in your toolbox that you can explore. Okay, so we're going to go ahead and play with the code over here, and now we want to do a little bit of plotting. So I'm going to add that, and we're just going to say here, visualization, I guess. Okay, this means we're going to use matplotlib. I believe we've used matplotlib in this Conda environment, so hopefully we won't have any problems. So let's just say now plot this. Okay, we're going to plot it. So now this is specific to 2 dimensions, but the way that this works is we're going to create basically a 2-dimensional Cartesian plane, so x and y, so xs and ys, for instance. We're going to create a couple of lists of this. So I'm going to do a list comprehension for w in DTM. Was it dr? Dr, right? So I'm going to iterate through it. And whenever I iterate through this one, it's basically like I'm grabbing the first vector, then the second vector, then the third vector. These are vectors of 2, so I need to grab them by index, right? So I'm going to say then, w 0, right? And then I grab the ones in that vector, the first one. So I just do the same thing for the second one here. So I'm going to say w1, oops, w1, and then a list comprehension for w in DTM, just like that. Okay, so we've done this part, and now we have our data kind of in a list. We can even print it if you'd like. So you can do like print xs, print ys, right? And we print out the data that we have. Now we're going to use matplotlib. So I'm just going to do import matplotlib.pyplot as PLT. Okay, and we're going to create a figure. PLT dot figure, right? And then now we're going to scatter this data into the plot. So I'm going to do PLT dot scatter, and I provide both the data in xs, comma ys, just like that. All right, so we provide this data, and then we can provide the labels. We know that these are the singular value decomposition 1 and singular value decomposition 2. So I'm going to do PLT dot X label, and it's going to be SVD SVD1, and then for the Y y label, these are just labels, names that I'm providing. So plt dot y label, we're going to say svd2. Okay, so we have these here. And basically plt dot show, like that. All right, so now that we have this, let's see if we can visualize it. So let's go ahead and run it. I'm going to do it clear. And there it is. So, do you guys see the graph? What do you see? Huh? 7 points, right? Each sentence is a point. Remember, each sample becomes a point in the vector space, okay? It's very important. We mapped it to 2 singular values, and then notice if I asked you to draw, so now I'm going to ask you as a human, right? I ask you, do you think that there are maybe 2 distinctive groups in that picture? You might say yes, right? One might be this one, and one might be that one. Do you see that? And so now you know that maybe these are the 4 sentences of data science. These possibly are the 2 sentences of sport, and this one is, probably just kind of in data science, but for whatever reason, it was put in this area. Do you see that? So that kind of allows us to, this allows us to basically to visualize. Now, as I said, don't expect this to work very well when you have millions of records, okay? It wouldn't. This is obviously, I've analyzed this problem quite a bit, and I know how it will turn out. But when you have your ADSB data, for instance, don't expect something like this. However, could you plot it? Yes. Do singular value decomposition. You could even do 3 dimensions, and then you get like a plot that's in 3D space, and that would also work. So if you want to have fancy graphs in your report, you can. All right. Now, what insight do you get out of it? You may not get that much. It just depends. Does this make sense, guys? Now, this tells you, though, that SVD1 and SVD2 are actually good features, right? The transformation is actually effective here. And, I would expect that the accuracy of the problem would only drop slightly from, let's say, 80% accuracy to like 75% accuracy, for instance, at most. All right, so that's the idea. So let's see what else we can do. So why is this important? What else can you do in this space? What else can you do in this space? Now, you guys know about Cartesian, go ahead. Euclidean distance. Very good answer. So you guys have known since you were in high school that you could do it. You learned that in high school, right? Cartesian planes, Euclidean distance. Think about Euclid, right? Who invented his equation, 1,000, 2,000 years ago, and it's still used today in AI, in pretty much everything, right? So that's amazing, first of all. But we can use Euclid's formula, Euclidean distance, or other distances like the Manhattan distance. A lot of those are just variations of the same idea to calculate distances between the points. So let's say that I had a new point and I draw it here, right? Like right there. You see that where the arrow is? Would you say it belongs to this group, or would you say it belongs to that group if the point is here? The right group. Why? Because you calculate Euclidean distances, and the distances would be shorter for that one than for that one, right? You see that? Perfect. So exactly, that's one of the beautiful things really about the vector space model, right? That it provides this incredible power to do things. Think about, you can take any problem in the world, model it like this, not even map it to 2 dimensions. You can perform the Euclidean distance calculation in a high dimensional space. You know, in R 10,000, you can still apply it. So that's what's so great about it. So let's do that. Let's do the similarity. So I'll show you a trick. So let's go back to the code. And let's try to do the similarity. This is a standard thing that you should always be aware of. I'm going to just remove the plot because I don't want to see that all the time. So now let's say that I want to do the Euclidean distances. And that is usually referred to as the similarity. Similarity. There's some other equations for this. So what equation we're using, it doesn't matter. Just be aware that it's kind of the same intuition. We're probably in this one using something called the cosine distance as opposed to the Euclidean distance. So they're basically equations based on the cosine function, but it provides this intuition of how similar the points are between each other. So what I'm going to do is I'm going to try to perform a matrix multiplication of this matrix, the 7 by 2 matrix. I am now going to multiply it times itself, right? With this idea of the similarity, and I'll be able to get basically all the distances between all the points, and then you'll see that some are closer than others, and that gives you some information. So to do that, I'm going to create similarity, and I'm going to say basically that I want to multiply DTM dr times DTM dr. In essence, that's what I'm doing, right? However, it doesn't quite just work like that. First of all, they have to be, I'm going to convert them into NumPy matrices, first of all. So I'm going to do here np dot as matrix, because this is in very much a linear algebra operation. So I'm going to do that for this one, and then for this one as well, as matrix. Do you see that? Huh? That's right. Very good catch. This is not going to work without a transpose. So then I have to do, for one of them, the transpose. And that basically is, as I said, so that the math works out. Don't worry about if you don't know what it's just a way of writing matrices correctly so that you can do a correct multiplication. You know what it's called sometimes the dot product, etc. So this idea then, and then finally the result of this, in parentheses, we're going to convert it into a array, a NumPy array. So NP as array. Okay, so this approach, this goes back to what we did at the beginning of the semester when we were playing around with tensors and NumPy arrays. All right, so now let's just go ahead. I want to make sure, let me double check. Make sure. Any mistakes? All right, so let's, first of all, let's just run this, the spot errors. All right, it ran, so that's good. So now that I have this, what I'm gonna do is I performed the multiplication, which means I have this idea now of similarities. And now what I wanna do is I want to print it out, all right? Obviously, you can also just extract this information and use it to compare points, right? To compare this sentence to that sentence. How close are they? So we're going to go back to the script over here. So let's scroll all the way down. And again, once again, I'm going to create a data frame using pandas for convenience so that it looks more readable and user-friendly. Data frame out of the similarity. Okay. We're going to say that the index is going to be example, right? The sentence. And the columns are also going to be example. Why is that? Well, remember, the matrix multiplication was between the points, right? We multiplied this point times this point. So what we're saying is, how close is this sentence to that sentence? You guys get it? Yeah? All right. So this is a very standard approach. Also, this operation should be pretty efficient in NumPy. It's the way to do it. It's fast. All right, there it is. So now this, unfortunately, just because the sentences are so long, right? It looks like that. So let me do something. Yeah, so I was hoping I could, I'm sure there's a way to like list them down, but it's not doing that. So anyway, we can see here that basically it's comparing machine learning is super fun to machine learning is super fun. And it's saying that, what's it saying? The closest, the strongest similarity is to itself, right? Do you guys see that? And then the weakest similarity would be to which one? I like football, right? And then intuitively, if you guys look at them, you would agree, correct? And then the other two that are most similar to machine learning is super fun are Python is super, super cool. And probably Python is great for machine learning, which makes sense because machine learning is in there. Let's look at the other one. So football is great to watch. Football is great to watch. So it's saying here, this is similar. It also found similarity here for whatever reason. Maybe the word great. So you have to keep in mind that we don't have that much statistics in there. You know, the more information we had, the better it would be. And then it found a relationship that was kind of the opposite for this one, right? Python is super, super cool. Does this make sense, guys? Guys, does this make sense? No? Yes? All right. So similarities. Obviously, we have the matrix for all 7. I'm sure there's a way to print them out. You guys can figure it out. Notice over here, this is a 7x7 matrix, right? Because it's comparing all these sentences to all the columns, which are the sentences. Any questions about this one? All right, so no questions. That's good. Sounds like you're understanding. So now we are ready then to do another thing. So if you remember, we looked at the original sentences here, and we said, oh yeah, by the way, these sentences, we see two groups in there, the sporty group and the data science group. You guys are able to figure that out because you're smart, but is there an algorithm that could actually do that for us? Okay, so we're gonna go ahead and now try to do this with an algorithm. So this introduces or takes us to the algorithm for today's class, which is the K-means algorithm, not to be confused with KNN. KNN is for supervised learning, for classification. K-means is for unsupervised learning and for clustering. Okay, again, if you want to learn how the algorithm works, the inner workings of it, I recommend you take ITS 365, which is the Intro to Machine Learning Foundations, where those algorithms are covered in that class here. This is an applied class, so we're just going to learn how to use it, okay? So let's go ahead and go back to the script here. So I'm going to scroll all the way down. All right, and so we're going to do an example. We're going to call it K-means. All right, algorithm. So we're going to, first of all, we're going to create a data set. All right, just a separate little data set kind of to visualize this. So let's do from sklearn.datasets import make blobs. And this is just a way of creating data randomly. So we'll play with that. We're also going to do, since we're going to use the K-means algorithm, we're going to need that library. So I'm going to do from sklearn.cluster import K-means. And that's the K-means clustering algorithm. Okay. So the first thing we want to do is create the data set, right? So create a data set here. So X comma Y, right? So this blobs actually gives you data with labels, but it's sort of generated randomly. So make blobs. We're going to say that we want n samples equal to, let's say, 200. So we're going to create 200 samples. Okay. We're just going to have two features so that we can visualize this. And it's consistent with SVD1 and SVD2. So we're going to say two features. And we're going to say centers, how many centers we want for the clusters, right? So we can say, for instance, 3. Okay, so we create, or we can play with that value. We're going to specify a cluster standard deviation for this data that we're generating of 0.5. Shuffle equal true. And a random state of 0. So it generates the data. Okay, so this should hopefully give us our data. So let's run this. Let me make sure it doesn't error out. All right. Oh, no mod. Oh, because I know we have used sklearn. So is it? Oh yeah, that's right. All right, so it worked. That's good. So that means we've created the data, just some data randomly so that we can first see it in action with some random data. So now we have it here. So what do we want to do now? Let's think. We've got a data set of 200. What's the matrix look like? It looks like 200 by 2, correct? It's 200 by 2, where the data basically follows 3 different distributions, because we said we wanted 3 clusters, okay? So we're generating this data intentionally to be in 3 clusters, clustered in 3 ways. So when we do the k-means, we could say 3, and it would give us, it would circle the 3 clusters, for instance. If we said 6, it would sit, it would do 6. So again, that algorithm is covered in 365, but it's pretty intuitive actually. So let's go ahead and plot this one, since we do have the plot before. So let's just do plot.grid and plot.show. And hopefully, all right, so let's try that one. All right, what is this? No, this is the 7 one. Oh, I'm sorry. I forgot to create the scatter plot. Yeah. So I printed the old one. Really here, we need to actually take the data and create a plot. So I'm going to do plot plt scatter. Yeah. And then in here, okay, so let's create, yeah, so we have our data in X. We have our data in X. So we need all the values, right? All the rows, the 200 in column 0, right? Feature 1, or the first feature. And then we also want all the rows, 200 in feature 2, okay? Just like that. So we've got our data now, and now we just need to specify some aspects of how we're going to plot it. So we're going to use color white, and we're going to use marker, just a circle, and the size is going to be 50. Just like that. Okay, so this should now have created our plot, and we can go ahead and plot our data. So let's try it. Or maybe not. Let me get rid of the old one. Comment this. Not working. So that's X and Y. That's the data. This should work. And I create plots. Okay. Any ideas, thoughts? The color, you think? Did you change it and it worked? But did you guys try it? Oh, it worked. Oh. Huh.
I was wondering because on the last one,
Yeah.
piece of the blue one was missing. I was wondering why it disappeared.
Oh.
Because of the white dots were overlaying.
Oh, okay. All right. I didn't see that. So let's try it. Ah. There we go. So do you guys see, right? So I just generated some random data. So it's easy. We've got our circles there. And if you notice, there's very clearly 3 groups in there. So this allows us now to try this out, right? So we're going to try out how to do the K-means algorithm. So I'm going to so that's the point now is to look at this data and try to do K-means. So I'm going to go back to the script. I have that little data set there. Okay, so now we're going to say, we're going to use the K, we're going to create, oops, sorry, yeah, K-means. So I'm going to create an object, KM, and it's going to be K-means n clusters. So n clusters equal 2 or 3, right? It depends on what you want. Let's just try 2. Okay. Then I'm going to init. And I need to specify some centroids. So that just means that I need to randomly pick a place where to start the algorithm in the space. So it's like you throw like a dart and just like start there. So I'm going to say, so we need to figure that out, but we can call it NP initial centroids. Comma. So in this case, I'm providing centroids. So I'm going to say n init equal 1. If we did this randomly, then we tell it how many random times it should try it before it settles on something. But for now, we're just going to say 1 because we're going to provide some centroids. Max iteration, that's the number of times that this is going to repeat until it finds a good solution. So we're going to say 300. And some kind of a tolerance of how close it should get. So we're going to say 1 e minus 0.4. So that's just a default value. And again, a random state. And let's just say 0. So that's a seed value. So at this point, we have the k-means pretty much defined. Now we're going to apply it. So we're going to predict some labels, right? So remember that visually, it'll change the color or something. But if we don't do it visually, we need basically the equivalent of a label. That is to say, now for every sample of the 200, they will be either in cluster 1 or cluster 2 or cluster 3. So that's equivalent to having labels, the Y, right? So we're going to say this. It's going to be a vector. So we take km fit underscore predict. And we're going to perform this analysis on the X data that we created recently. And then we just print out Y underscore km, and that should give us the labels. Does this make sense, guys, how this works? So that's the basic idea. Now the centroids, I need to specify them. Now, obviously, this would be tedious to do. So I'm only going to show you, but then we're going to try to switch to randomly. So initial centroids equal, and then we need to, so I said 2 clusters, so we need 2 centroids. Oops. So the first centroid will be, let's say, just some random numbers, so 8,7. And then the next one will be 2,8. The coordinates, remember this is a 2. The dimensionality of this space is 2. And then we need to take this initial centroids and convert it into a NumPy array. So NP initial underscore centroids is going to be np.array. And we specify in there initial centroids. We can also specify the data types. So in this case, float 64, for instance. You guys see that? So that's the basic idea. So now let's go ahead. So I'm going to do Control X, Y. Run it. Okay, so that's the data as we had it. And now, even error. I'm missing a comma here. Okay, so now let's go ahead again. And there they are. You guys see this? So how many of these do you think we have in here? These are the labels, right? For each point in X. So how many? 200, exactly, because there are 200 samples in that space. Each one now has a label, which means each one of those samples has been assigned to either cluster 1 or cluster 2. See, this is an automatic way of getting labels from your data by just using K-means. Is this great? I mean, not necessarily, but it's certainly clustering and what you can do with unsupervised. Now, in our case, what we want to see is if it assigns class 0 to the first 5 sentences and class 1 to the other 2 sentences, right? You guys see that? That's what our goal is. So now let's switch over to random. So I'm going to go over here. And I'm just going to say in here, instead of this, I'm going to say random. So add a comma and then comment out this. And then here now we're going to say 10 because we wanted to do this 10 times iteratively. All right, so this way we discard these centroids. We don't have to calculate them anymore. The algorithm should do it for us. And there you go. It worked. Does this make sense? All right, so now what we might want to do is before now the next step obviously would be to apply the algorithm to our original data, the sentences. But before we do that, let's see if we can't plot this data just to show how this would work. So let's think. So let's create right, let's do a new scatter plot here. So see if we can't see change the color given these Y's now. All right, so I'm going to do plot.scatter. Okay, and I'm going to take the data in X, and I need to slice it intelligently, right? So I need the X and Y for all the points that are of class 0, right? That's the first thing I'm going to need. So I know this part. This is 0. And then this is 1. But I only want the ones where they belong to class 0, not class 1. Now this data is in y_km, right? The labels that we just predicted over here. So that's what we have. So we've done this before, I think. We can just take y_km and we say equal to 0. So those that are equal to 0, this operation will return the index for them. And now we have the index of the, because they correspond, right? The x's to the y, there's 200 x's, 200 y's. It'll give us the index in the x, and then now we have the samples that are equal to 0. Does this make sense? So we do that here as well. So I'm going to do y underscore km equal what? What's the value here? Not 1, 0. These are only the ones for class 0, but we need both the x and the y because the x and the y allow us to plot a point. Right? So these are just the samples for that. Let's add the commas because I keep forgetting that. All right, and then now that we have this, it's just like we did before. We're going to say size equal 50. We're also going to say other colors, right? Color, light green. Comma. Another marker. So I think this is the star marker. We'll see. And then we're going to provide a label for this one. Label equal cluster 1. Okay. We're going to repeat the exercise, but for the second class that was determined by Kmeans. So this one's going to be x again. Again, we need the 0 and the 1 coordinates. So this is 0. This is x, comma 1, because we need the y coordinate. But now we need all the ones that are class 1 or the label 1 or the cluster 1 as it was determined by the Kmeans. So that's going to be what? Y underscore km equal what? What is this one equal to? 1. Remember, this is the other group. What about this one? 1. Does this make sense, guys? So we're getting the data for the two groups by slicing. And then now we just have to say size equals 50. Color, a different color. Orange, let's say. The marker is going to be an O. And label cluster 2. Label cluster 2. All right. So now I have this. So the graph, we have the scatters. Now let's do plt.legend, plt.grid, and plt.show. All right, let's see if that works. So let's go ahead, Control X, Y. So that's our original plot, right? And then now, moment of truth, there it is. Make sense? it worked, right? K means we set 2 clusters. There it is, 2 clusters. Now, if we did 3 clusters, with the tricky part, I leave that for you guys to do on your own, not as homework, but just do it, is you don't really have to change K-means, right, that much. You would just go in over here, say, well, this is the blob. So then you would go here and say that you want 3 here. You see that? You want 3 there. But the trick is to plot it. You will need to have, see, this scatter is for 0. This scatter is for 1. So you will need another one for 2. Got it? And that should be about all that you need. So I'm pretty sure you can do that on your own. We're short on time, so I just want to finish the rest, right? The last part. So this you should be able to do on your own, but it worked. All right, the last part of this is basically now what we want to do. So I'm going to close this one. We want to cluster these 7 sentences, right? So that we can arrive at 2 groups. All right, for the sentences. So we're going to go back into our script. And now this is now finally we get to cluster our data. So we're going to say here cluster sentences. Okay. So we're going to create K-means. DR, but now it's going to be K-means. We want 2 clusters. We want 2 clusters. Init, we're going to init randomly. Learn. We're going to do 10 random starts. So 10, oops, no, sorry. Init equal 10. Number of iterations for this one, let's say 300 again. 300. Tolerance again, same value as before, just default 1e minus 0.4. And random state equals 0. All right, so it's just pretty much the same thing we had done before. We have the same algorithm. Now we do the y's, let's call it y dr. And it's going to be km dr dot fit underscore predict. Again, with our DTM dr. So our original data. Notice now we are using, instead of the meg blobs data, we're using the actual DTM data with the sentences. So this is our 7x2, right? Or our 7 by, you can use the 7x2. What name did we give that one? That was DTM dr with 2. Or the original one, which was just DTM, right? So DTM or DTM dr. So either one, you can play with it. Should work. So now let's do, basically now we should have the labels, right? We should now at this time have our labels. So let's print them. So I'm going to do print y dr. Control X, Y. That's the three blobs. We can actually get rid of that graph and that one. There it is. Do you guys see that? There's 7 now. Now, did it do it right? Do you think? No. The first 5 should be zeros. The last 2 should be 1s. Do you guys agree? Just intuitively, you can see that. What's the problem? The make blobs has 200 samples. It's better data. It was done with a statistical distribution, literally, right? This data is only 7 sentences. There's only 13 words. It's not that great. Do you see that? So there lies the problem. However, let me show you something very interesting. I'm going to play with this to make the frequency stronger. I'm going to play with the sentences to make them to distinguish the 2 distributions a little bit more. How am I going to do that? Well, I know that these 2 sentences belong to sports. Like, so I like football and football is great to watch. So what I'm going to say is I like to watch football. You see, now I'm making them stronger. Football is great to watch and I like it. Now notice over here, I'm going to make these stronger also. I'm going to say machine learning is super fun and statistics are cool. Python is super, super cool and great for data science. Do you see what I'm doing? I'm kind of making them more similar. Statistics is cool too. And machine learning is super. Data science is fun with Python. Notice that I'm careful to only use words from like the group, right? So I'm using the 5, the words in the 5 sentences, and I'm now just like making it richer in the distribution. And this actually should prove that if the distributions are better, like more unique, the algorithm will do well. Data science is fun with Python. Python is great for machine learning and statistics, let's say. Right? Kind of makes sense? You guys understand what I'm doing? So let's try this one. Run it. Right. You see what I did? Did it work or no? What do you guys say? The first 5 sentences are 1. The other 2 sentences are 0, right? So the sporty sentences were basically correctly labeled, and the 5 first sentences were correctly labeled into a group. Do you see what happened there? I like to do this exercise because it proves that if you have, again, if the data are like in similar distributions, remember here it's frequency distributions of the words. they kind of, you can basically do things like this correctly. We were able, just by making them a little bit richer and more, having more words in common, we were able to correctly assign the label. Now, you can't always do this with the data, right? So usually you have to use the data that you get. You can't just go in and manipulate the data. This is just an example I use. But hopefully when you use something like Twitter, if you have 1 million records of Twitter, okay, of good sentences with little noise, well, it's a similar idea. So what I did by adding words is equivalent to just, instead of having 2,000 Twitter samples, have 1 million. You're going to have more richness of what you're looking for. Is this clear, guys? All right, perfect. So no questions? All right, and the last exercise of plotting this with graph, I leave that to you guys. I'm pretty sure you can do it because it's exactly as it was with make blobs. And that's it. So that concludes today's topic, which is unsupervised learning. Okay, what we're gonna do now next week is we'll probably take that make blobs or something like that as data and create a tensor to feed into PyTorch. Do you guys see that? So that would be the last part of this. You collect the data. Now, hopefully you realize you've learned a lot today, right? So you have the features, the original bag of words, you compressed it, you transformed it into singular values. You learned that you can visualize, you learned that you can reduce the dimensionality. But the key thing that I want you to understand is this, right? That you can take any data and create the matrix, right? That will be converted into a tensor and feed into your machine learning algorithms for supervised learning. So in fact, right now, for instance, if I look at this, right now, after this step, I have the labels here, right? The 7 labels in this case. And in DTMR, what do I have? I have the data. So here's the X, and this is the Y, right? I have a matrix that it's 7 by 2 or 7 by 13, and then I have a matrix that is 7 by 1. Yes? So this is my Y, this is my X. What we're gonna do next week is I'm gonna take those, convert them into tensors, PyTorch tensors, and then I'm gonna use that X and Y to train a deep neural network. Okay, guys? And that should hopefully show you a lot of the steps for taking raw data like social media, HTML, RSS feeds, Twitter, etc., and training a deep neural network. Okay, so your project should be similar to this, obviously. However, the labels here, we're doing it with unsupervised learning. I will just use that as a convenience for my demo on Monday. You guys would be you have to do the actual annotation by hand for part B of your project. Is that clear, guys? And then for, as I said, for part A, the idea of the ADSB data, well, you need to use a lot of data. So hopefully pick one of the parameters in the ADSB data that you can use as the label. That way it's already annotated for you, and you can use millions of records if you have to. All right, so that's basically it. Please don't forget to submit your assignment. That's due tonight. Your Twitter assignment is due a week from today, and everything I think is good. And then we'll stop here for today. So I'll see you guys on Monday.